Okay, so now we're going to look at the relationship between the derivative of a function and the shape of its graph and how those are related. So we're going to be looking at the first derivatives and second derivatives and understanding the implications as far as like the appearance of the curve and the values of these derivatives. Okay, so first we have this increasing decreasing test. And this is just about looking at the first derivative and seeing if it's positive or negative. That tells us if the first derivative of the function at a point is positive, that means that the function is increasing at that point. Or if it's positive on some interval, it's an increasing function everywhere on that interval. If the first derivative is negative on some interval, then the function is decreasing on that interval. Okay, let's take an example. Let's look at this function 3x to the fourth minus 4x to the third minus 12x squared plus 5. Well, if we look at the first derivative, f prime of x is 12x to the third minus 12x squared minus 24x, right? And if we wanted to look at see when is this positive or negative, let's factor this a little bit. This is 12x times x squared minus x minus 1. And we can factor that even further. 12x times x, let's see, minus 2. Okay, so you can see if we could factor this further, 12x times x, let's see, that would be x minus 2 times x plus 1. So if you look at if you think about the sign of this thing, it's going to change at 0, it's going to change at positive 2, and it's going to change at negative 1. This x to the third function, so this is f prime of x. I'm going to look at, I call this a sign, S-I-G-N, sign, like positive negative sign graph. You can see that this thing is going to be, since it's x to the third, it basically looks like this. This is kind of what it looks like. It's increasing. I know this is going to be, it has an increasing slope. Sorry, the function is going to go up to infinity, and it goes down to negative infinity, and it changes to positive and it changes to negative. So the sign of this changes every time it has an intersection. This is kind of what it looks like. It's changing here roughly at negative 1, 0, and 2. That's kind of what this thing looks like. So the first derivative is negative, then it's positive, then it's negative, then it's positive. So f of x is increasing on the intervals where the first derivative is positive. That's from negative 1 to 0 and union 2 to infinity. F of x is decreasing on the intervals where the first derivative is negative. That's negative infinity up to negative 1, union with 0 to 2. Okay, so now we have something we're calling the first derivative test. So if you have a critical point, a critical number on a continuous function f, if the first derivative changes from a positive to a negative at that c, then f is going to be a local maximum, has a local maximum at c, or c represents the local maximum point on the graph. If the derivative changes from negative to positive, then the function has a local minimum at c. And if the sign doesn't change, then that means it's neither a local maximum nor a local minimum. It's neither. So and that happens sometimes, an example of that would be the cubic function x to the third. The first derivative is going to be 0 at x equals 0, but you'd see that actually the first derivative is going to be positive on either side of that. So there's not a sign change, and so and you know exactly what I'm talking about. That looks like, that's pretty sloppy, but that's not a local minimum or a local maximum. Okay, so let's continue this example. Let's find the local minimum and the local maximum values of this function. So if you recall, we found that the derivative changed from negative to positive at -1. That means because it changed from negative to positive, that means f prime at -1 is a local minimum. Because it changes from positive to negative when x is at 0, f prime, sorry, I should fix that. It's f of -1 is a local minimum. F of 0 is a local maximum, and because it goes from negative to positive at 2, that means f of 2 is a local minimum. And we can just plug those numbers in, and you get f of -1 is 0, f of 0 is 5, and f of 2 is -27. Just trust me. So yeah, so these are the local maximum and local minimum values of the. Should actually say that these are the local minimum value. Yeah, that looks good. Okay, now let's take a look at another function. Let's find the local maximum and minimum values of this other function, g of x equals x plus 2 sine of x over the interval from 0 to 2 pi. So the derivative of g is going to be 1 plus 2 cosine of x. All right. So let's find see if there's any times when this is equal to 0. 1 plus 2 cosine x equals 0. Well, that's when the 2 cosine of x is equal to -1, otherwise known as cosine of x equals -1/2. In a unit circle, the cosine is going to be equal to -1/2 at 2 points on the unit circle. So that's the cosine is the x-coordinate. I know my unit circle is a little sloppy, but we only care about the left-hand side of it. These are the two angles, and if those are that's pi. That's 2/3 pi, and that's 4/3 pi. So x is going to be 2/3 times pi, and I should say or 4 pi over 3. Now, these let's look at the sine graph of g prime of x between 0, 2 pi, and these two values. That's 2 pi over 3 and 4 pi over 3. What is the first derivative going to be positive or negative? Well, let's see. If you plug in 0 for cosine, you're going to get a 1, so that's going to be positive. But when you get to 2/3, then you get -1/2. It's going to be 0, and then it's going to switch over to being negative for a while. And then when you get to 4/3, it's 0, and then you get to some point between. I guess you could check some value, like you could plug in something like 3 pi over 2, like 3, yeah, and you'd find it's going to be positive once again, because once you get to 2 pi, of course, this is positive once again. So yeah, you can see that that's going to be the case. So that means that we have g of 2 pi over 3, which is 2 pi over 3 plus 2 times, what's the sine of 2 pi over 3? That's going to be root 3 over 2. This is a local, let's see, the first derivative is positive, then it's negative, that's a local, so it's like the function goes up and then it comes down. And here it's going down and then it goes up again. That's kind of the picture. That's why you have a local maximum and a local minimum, respectively. This is a local maximum. And g of 4 pi over 3, that's going to be 4 pi over 3 plus 2 times, let's see, that's going to be negative root 3 over 2, is a local minimum value. Yeah, there you go. Okay, so now we're going to talk a little bit about concavity. So if a graph of if a function the graph of the function lies above all of its tangents on an interval, it's called concave upward. So this is what we're talking about, like here. So the tangent lines I'm going to put in red. All of the tangent lines are going to be like that. This is concave upward. If the curve has the other kind of shape like this, where it's going to be the curve is below its tangent lines, like here's a tangent line, here's another tangent line, here's a tangent line, it's below, it's concave downward. Okay, so we'll talk about concave upward and concave downward. So they're over intervals, the concavity might be upward concavity or downward. So if a point on the curve is called an inflection point if that's as long as the curve is a continuous and differentiable curve. It's an inflection. Actually, I don't think it needs to be differentiable. It's just as long as it's continuous and the curve changes from concave upward to concave downward at that point P. So this is an example of what a inflection point would look like, where you have downward concavity on one side and you have upward concavity on the other side. That's an inflection point. So it turns out that the second derivative tells us about concavity. And similar to with the slope, it tells that told you about increasing, decreasing. Well, if the second derivative is positive, then the graph is concave upward on some interval I. And if the second derivative is negative on an interval, then we have downward concavity. Okay, so we're going to attempt to sketch a possible graph that satisfies the following conditions. In fact, let's get some grid here. We want the first derivative to be positive from negative infinity to 1, and I want it to be negative from 1 to infinity. Let's draw our axis here. Now, let's sketch a possible graph that satisfies the following. I want to have the first derivative to be positive from negative infinity to 1. I'm going to actually draw a little chart that tells me about the conditions I want. At 1, I'm going to have things change with the first derivative. I want to have a positive first derivative, which means I want it to be increasing. And then I want to have this thing have a negative first derivative from 1 to infinity, so it's going to start decreasing. Okay, now the second derivative, I'll mark its kind of changes down here, it's going to be positive from negative infinity to negative 2. A positive second derivative means concave up. From 2 to infinity, the same thing, concave up. From f double prime is negative from negative 2 to 2, so it's going to have that kind of concavity, downward concavity. And the limit of f is, as x goes to negative infinity, is negative 2. So that's something that I'm going to put as an asymptote. And the limit is going to be 0 on the other side. So I'll kind of put that here. Now, as x goes to positive infinity, the function levels off at 0. So I want to, there's many possibilities here, but the things I want to look out for is things happening at 1, right? Things are happening at 2 and at negative 2. I want to have inflection points at 2 and negative 2. That's where the concavity changes. And I need to make sure that, so I'll just plot a couple of points where things might might be. I want to have the first derivative to be 0 when I'm at 1. So I'm going to, when I have the inflection point, there should be 0 concavity. So it should kind of straighten out. So I'll do this in green. I'm going to have a straight line that kind of curves and makes that kind of shape. Now I want, that's the downward concavity. I've got the horizontal here, so we have, it's increasing here and it's going to be decreasing there. It's going to level off, so I'm going to have it continue, and it's going to have this kind of a shape to it. On that side, on the other side, it's going to have this kind of a shape. It's concave up, so it's going to be sort of increasing and reaches to there. So this is the concave up part. And yeah, this has all the features. It's a little bit ugly looking, but it does have everything that I was looking for. Okay, now let's look at another curve. Y equals x to the 4th minus 4x to the 3rd. Thinking about concavity, points of inflection, and so forth. Well, okay, let's look at y prime. This is going to be 4x to the 3rd minus 12x squared, and the second derivative is 12x squared minus 24x. I'm interested in looking at the first derivative. This can be factored, and I'm going to factor it. Take out the 4x squared, and what I'm left with is x minus a 3. So the first derivative has a change at 0, and it has a change at 3. Now, this is going to so because I factored out x squared, the first derivative doesn't change sign at 0. Okay, let's think about, let's just plug in a value. Let's plug in 1. So you plug in 1, you're going to get 4 times 1 times 1 minus 3. That's negative. So this is negative here. It changes sign after 3, so it becomes positive, but it doesn't change sign at 0. It stays negative on both sides of 0. So we have a local minimum at x equals 3, and it levels off at x equals 0, decreasing on negative infinity to 0, union 0 to 3. It's increasing on 3 to infinity. Okay. Now thinking about the second derivative, if we factor this one, which we will do, factor out a 12x, what I'm getting left is x minus 2. And so we have, this is not a straight line. Let's draw that straight. That's even worse. All right, that's good enough. The second derivative has a change at 0 and at 2. It looks like what we're going to have is the second derivative is going to be, at the high end, it's going to be positive. Here it's going to be negative and positive. That means it's going to be concave up, concave down, concave up. And again, this is going to be a decreasing function, it's decreasing function, and then it's going to be increasing. So let's try to sketch this thing. Now it might be worth plugging in just a point to have some anchor point. And it's pretty clear that when x is equal to 0, then y is equal to 0. I'll put a couple guides in yellow. I want this thing to be decreasing. I want it to decrease some more. Actually, it's going to decrease, but it's going to level off at 3, and it's going to start increasing after that. I'll put in red my concavity, and I have this thing. I want to have kind of this kind of concavity until 0, and then I want to have a downward concavity, let's see, between 0 and 2, and then I'm going to have the upward concavity. I guess I'll probably have something more like that. So I'm going to try to have a sketch that has all these things. I want to have this thing level off for just a moment. I didn't draw that, but this is what's happening here. It's going to level off for just a moment, but it has this upward concavity. That's where concavity is changing. So it kind of does that. It's going to have an inflection point. It's going to come to a local minimum. I could put the local minimum anywhere. I didn't really, I'm not evaluating it, so I don't know the exact point. But I need to make sure that that the concavity is changing. So here's where it's going to be concave upward. Oh, I'll make it a little less steep. Okay, it kind of goes like that. And I'm going to make sure this is concave downward here. Okay, so here's the point where the concavity changes. Concavity is upward. Okay, this does everything I need it to do. Yeah. And you can see what we got. This is pretty decent. I sometimes draw these little lines at the inflection points. This is an inflection point. Concavity is changing there. Okay, I think that's probably good enough for now. We'll end here, and we'll just do more of this practice in class, understanding using this first derivative and second derivative tests to understand the shapes of these graphs. All right, bye.